Welcome to This Explainer. Today, we're unpacking one of the absolute most fundamental forces in physics. We're going to look at how it governs literally everything, from our daily lives right here on Earth, all the way up to our greatest ambitions in the stars. We're demystifying momentum and seeing exactly how space engineers use it to conquer the vacuum of space.
So let's just dive right into this with a kind of deceptively simple question. What do a massive runaway truck barreling down a highway and a spacecraft soaring in orbit actually have in common? I mean, on the surface, they seemed completely unrelated, right? One is stuck dealing with the friction of asphalt and gravity, and the other is just floating in a weightless vacuum. But the invisible physics dictating how hard it is to stop both of them, they are exactly the same.
Section 1. The basics of momentum. Understanding the rules. To properly answer that question, we first need to establish a few ground rules.
Let's do a quick comparison to refresh our memory on how momentum works. Imagine a tennis ball moving at 50 kilometers per hour. You could probably catch it pretty easily, right? Now imagine a heavy truck moving at that exact same speed. Trying to stop that truck would be physically impossible. It's a no-go. Even though both objects share the exact same speed, the immense mass of the truck makes it incredibly hard to stop. So it's really both mass and velocity that dictate the physical reality of moving objects.
That brings us to our golden rule. Momentum is governed by a simple but incredibly powerful equation: mass multiplied by velocity. It's a mathematical absolute. This means a heavier object, or a faster object, intrinsically has more momentum. But, and this is the crazy part, it also means that even a tremendously massive truck has absolutely zero momentum if its velocity is zero. If it's just parked on the side of the road, its momentum literally doesn't exist.
Section 2. The Law of Conservation. An unbreakable rule. Let's introduce the ultimate rule of the universe that our space engineers always have to play by.
The absolute nature of this rule is just fascinating. Quote, "In an isolated system with no external forces, total momentum remains constant." End quote. Basically, what this tells us is that momentum is essentially a cosmic currency. It can be traded, it can be transferred between different objects, but the total amount in the system always stays exactly the same, unless some outside force interferes. You can never just make momentum disappear out of thin air. You can only move it around. To really visualize this, imagine an everyday example. Picture two ice skaters standing perfectly still, facing each other on completely frictionless ice. Right now, their velocity is zero, so their combined momentum is also zero. Now one skater pushes the other. Boom. Because of that push, both skaters instantly start sliding apart in opposite directions. And here's the cool part. Even if one skater is much lighter and shoots backward way faster than the heavier one, the math perfectly balances out. The positive and negative momentum cancel each other out entirely, leaving the total system perfectly balanced at zero.
Section 3. How rockets actually fly. Translating force. Let's see how this nice, neat equation translates into absolute brute force.
Now, it's a super common misconception that rockets fly by pushing against the air. But out in space, there's no air. So how on earth do they move? Well, a rocket engine burns fuel to create these intensely hot exhaust gases, and then it expels those gases downward at mind-boggling speeds. Just like the skater pushing their partner, the exhaust gains a massive amount of downward momentum. And to conserve the momentum of the system, the rocket absolutely must gain an equal amount of upward momentum. Rockets don't push against the environment, they just aggressively throw mass backward to forcefully propel themselves forward. Let's look at a truly legendary space engineering example. The Saturn V rocket, the one that famously carried astronauts to the moon, was unfathomably heavy. To get that massive structure off the launch pad, it had to generate a terrifying amount of upward momentum. It pulled this off by ejecting over 13,000 kilograms of exhaust every single second. By throwing that immense mass downward at blistering speeds, the Saturn V generated the enormous reciprocal momentum required to lift it entirely off the Earth. It is literally the ice skater principle, just scaled up to the most extreme degree imaginable.
Section 4. The delicate docking dance. Neutralizing hazards. Because launching is really only half the battle. Once we're actually in space, momentum transforms from this powerful engine that gets us there into a critical hazard we have to very carefully neutralize. When two spacecrafts need to physically connect or dock in orbit, they're usually traveling around the Earth at thousands of kilometers per hour. But relative to each other, they have to travel at nearly the exact same speed.
Reducing their relative velocity to almost zero, we're talking literally just a few centimeters per second, is absolutely the only way to safely dock. If one spacecraft approaches even slightly too quickly, it carries way too much momentum, and that resulting impact could severely damage the docking mechanisms, or worse, completely destroy both spacecraft. For instance, look at how the SpaceX Dragon approaches the International Space Station. It doesn't just fly up and hit the brakes. No way. It approaches extremely slowly. It uses a network of these very small thrusters to meticulously adjust its momentum, puff by puff, carefully bringing that relative motion down until it is safely eliminated. It's a slow, super methodical neutralization of momentum to ensure a completely safe connection in a really harsh environment.
Section 5. Mastering space engineering. The bigger picture. Let's zoom out for a second and look at the whole shebang.
Because momentum is conserved and entirely predictable through mass and velocity, it is the absolute foundation of all modern orbital operations. Beyond just launching off a pad and docking at a station, engineers use these exact momentum calculations to predict and avoid catastrophic spacecraft collisions in orbit. They use it to precisely program robotic arms so they don't accidentally rip themselves apart during delicate satellite servicing. And they use it to figure out how to safely capture and remove dangerous space debris. Seriously, without a perfect grasp of momentum, working in space would be entirely impossible.
Okay, let's quickly review our key takeaways. Momentum always depends on mass multiplied by velocity. Total momentum is always conserved unless an outside force acts on it. Rockets exploit this exact conservation to fly in a vacuum by forcefully ejecting exhaust backward, and safe satellite docking demands incredibly careful control of that exact same momentum.
Which leaves us with this final thought. Knowing that the conservation of momentum dictates almost every single spacecraft maneuver we currently rely on to survive in Earth's orbit, how will we engineer these exact same invisible rules to travel even further? When we finally set our sights on neighboring star systems, how will we manipulate the simple relationship between mass and velocity to bridge the impossible distances of interstellar travel? It's a massive challenge of momentum, and it's one the next generation of space engineers is going to have to solve.